So let's get started. What we were going to do today, I sort of sketched this in a slightly different way than some of the other canonical stuff. And I'd sort of like your feedback at the end in terms of what you think about this. So what I did for today, so we've kind of covered some of the basic underlying ideas of kind of the formalism of estimating stuff non-parametrically. And what I wanted to do today was, last time we were kind of talking about the assumptions for RD, we talked about the basics for estimation. And what I really wanted to do today was a version of trying to talk about, like, if I was going to write an RD paper, what would be the list of things that you really need to do in order to write said paper? I'm realizing I could kind of do this for a variety of the stuff that we've covered over the last couple ones. Is we can almost just say we had this identification design, what would be all the things that one would need to write or do? Kind of independent of the economic content, of course, that you're going to put in there, is just the idea of let's make a checklist of what are the kind of the supporting points that one needs to make. Obviously, it's important to understand kind of the econometrics of what's going on, but I also wanted to give a sense of kind of the artisanship of what one would do here. So let's go through it, and at the end, I'd be sort of interested to know what you think of this. This is a sort of thing where you never want to follow something blindly, but I do get the sense, especially as a graduate student, I think you're trying to figure out, like, what is it exactly that I want to be doing for this paper? Like, what are people expecting? And so this is hopefully gives you a sense of what it would be. So the running example we'll have through a lot of this, I'm going to be using the data from this paper, is that Lee 2008 paper, basically the impact of a Democrat winning a subsequent victory in an election. So the running variable here, as a reminder, it's the vote share margin of victory. So for a Democrat, so the idea is, if you win, so that's if you're right above what you need to win, the margin of victory. That's the running variable, is this vote share. D is obviously the winning of an election. It's a sharp RD setting. And the outcome in this one, there's a number of outcomes, but for this one, it's the subsequent victory in an election. So next time you go up for an election, so in the House, for example, what's the probability that you're going to win subsequently? And so there's this obvious point that if you win, you're then much more likely to win subsequently. There's a number of outcomes you could like. It's not just that one. Kind of the reason why there's that strong effect is you're obviously much more likely to run if you're the incumbent, and incumbents tend to have a victory. They tend to be more likely to win elections as well. And you also just get a larger vote share as well. So this is the vote share in election. This is kind of the outcome we're going to be focused on, is this continuous measure, which is, what share of the popular vote do you get in the subsequent election conditional on having won? You see this discontinuous jump that occurs here. So that's kind of the treatment effect in this setting, and it's what our example is going to be for a number of the stuff that we're going to do. And now we're saying, all right, imagine we were going to write Lee 2008, independent of, there's some really nice econometric stuff in that paper that has to do with thinking about what the permutation test is, but just purely, I want to show this effect. What would be the things that I'd want to do to support my design, and basically in order to convince folks of what I was doing from a purely an estimation perspective. So I'll read you kind of the list, and then we're just going to go through it. And along the way, we're going to talk about a number of different papers that are relevant for what you're interested in. And obviously, feel free to jump in if anything isn't clear. So the first thing is, what you're trying to do first is convince the reader or the audience member of basically the validity of your design. So there's kind of two ways to think about this. Is the checklist, you obviously can do this in different order. My preference is to kind of establish the validity of the design first before going into what all the estimates are. Sometimes people like to be like, here's my effect, and then I'm going to show you a bunch of ways in which it's robust and why you should believe it. Those are rhetorically different things, but conceptually have the same content in them. But really what you want to do is do a graphical representation and test of balance of things that you would typically think of as effectively being excluded characteristics that wouldn't be affected by your treatment. So think, pre-treatment characteristics, things that you think shouldn't be economically affected, et cetera. and also potentially your quote unquote first stage, like your treatment, if it's something that is fuzzily manipulated. So if it's something where you go across the boundary and you're much more likely to have take up, but it's not 0, 1, that's your first stage for a fuzzy RD. The next thing you want to do is, so this test of balance, a lot of time, and we'll get into this, is thinking about differences in mean. So the continuity of the expected value of your characteristic as you go across the boundary. So in this context, that's just looking at the continuity in the conditional mean function. What we're going to talk about today is a nice paper by Canonical out there that looks at this permutation test. So you can do kind of a stronger test of this characteristic by looking at the full distribution and using basically a randomization permutation approach. And that's just another way of kind of testing for the balance of these characteristics. You can then look at the density of the forcing variable, and this came up last week when we were talking about this design, is you can check for the density of the forcing variable. So what that means is, if there's something really special that's happening at 0, you might imagine that people manipulate themselves onto one side or the other of the boundary in order to get a higher, basically get the treatment or stay away from the treatment. That's a very natural economic response. And then last check you might do is think about placebo checks. And so this obviously would go hand in hand with the actual estimation. But if there's a cutoff at 0, what you might do is try the cutoff at -25 and show that there's no effect there. Basically, that it's smoothly continuous there to kind of show, and you can do this at a bunch of places throughout the running variable distribution and show how the jump that you detect compares relative to what you might have just gotten from random noise, for example. That's a very kind of compelling way to show this, although there's sort of slightly less formal language about that in a lot of work that people do. Then, as what we've already, as what we've already talked about, you want to have kind of a graphical representation of the outcomes. So this is what we've already seen and we've talked about. And then you want to give estimates based on kind of optimal bandwidth choice, robust inference, and using local linear analysis, local linear regression. So these decisions that I'm talking about here really depend on the running variable. If you have a discrete running variable, you need to kind of account for the discreteness. This is this very nice paper by Michael Colasar and Roth in 2018 in the AER about discrete running variables. We're going to talk about that on Thursday specifically. I spent so much time just on the continuous example that I just am focused on the continuous example today, but it's a lot of things simplify in the discrete case, but then some things get more complicated in the discrete one. And then the second thing, kind of based on these choices, is that I'm really going to hammer the idea that you should be using local linear regression, so that kernel regression, rather than global polynomials, which I think historically has been a little bit more common. But I think there's pretty compelling evidence from this Gelman and Imben's paper. It should have a year on it, but it's on the syllabus. That basically saying that you really want to be using local linear regressions because of this sensitivity to extreme values from these global polynomials. And I'll talk about what I mean by global polynomials when we get back to that. And then I want to just briefly mention about how you should think about robustness analysis along bandwidth choice and other tuning parameters and how to present it. Any questions on that? This is obviously just a checklist. I haven't told you anything meaningful yet. Okay, cool. So let's talk about checking for balance. So one of the issues, kind of similar to all of the settings where we're thinking about causal inference, is that this is all fundamentally not a testable assumption. There are things that are not consistent with the identifying assumption, but it's not inherently testable per se, in the sense that if you can't basically show evidence that it necessarily passes. You can only ever kind of fail to reject that your identification strategy is satisfied. So that's fine, but that means that we kind of have started to develop a language of things that we want to look for when we're doing this appropriately. And so in the RD case, conceptually, this should be Lee 2008. What we want to do is, in the RD setting, it's very natural to think that there should be characteristics that are effectively going to be smooth through the discontinuity. So with the idea that, so what Lee basically talks about is, unlike in the traditional RD setting, really the idea is that, well, there should effectively be kind of a smoothness in the characteristics across the boundary because people can't fully manipulate themselves onto one side or the other. Meaning that, look, when we look at people who basically, so let's just imagine it's the type of people running for office, that characteristic should be smooth, continuous through the boundary in the same way that we would in the opposite way, that we would expect the outcome to change just continuously there. What we're asking is that, if you remember, the identifying assumption from the Vanderklaw paper and from the Hahn, Todd, and Vanderklaw paper was that if we took E of y0 conditional on z and E of y1, I guess it makes more sense to put y1 up here. I'll change the camera in just a second. That, here they are, here's the cutoff. The idea is that these are smooth through this. The potential outcome is smooth through that characteristic. And so as a consequence, what we can do is identify the effect at exactly that point, because these mean value functions are continuous, right? So there's this function here. Oh, wow. This pen is dead. That's how you know the pandemic has been really long. I've managed to go through all my whiteboard pens. So this one is smooth, and this one is smooth. And what we get is that obviously that our function discontinuously changes, but the underlying unobserved characteristics are smooth. And so conceptually is the idea that, well, then there's also some W here that should move smoothly through this. And with the idea being that, if that weren't the case, that's really inconsistent with the identifying experiment, which is that, these underlying characteristics, if this is a characteristic we think affects the potential outcome, then that one should also be smooth, because it's going to basically, if it changes continuously, you'd imagine the underlying potential outcomes also change discontinuously. Is that clear? Presumably that makes sense, right? It's like, I don't think I'm blowing anyone's mind. It's like the idea of what you'd like is that it's approximating a random experiment. And so at this boundary, it would make sense that the characteristics between the two groups should effectively look the same. And so you would have that same aspect that would happen in any random design show up. It's not quite right to say that it's randomly assigned, right? So like, it's not a random assignment on the left and on the right. It's only really at that one point. But the idea is that if you take the conditional means or the characteristics and you move them close to the center, that's where you're going to, they should effectively be continuous and smooth across that. So a natural run in this Lee paper, right, is that, or a natural assumption in the Lee paper is that if we're looking at the vote share in period T, that the probability of victory for, say, a Democrat in the prior election should be smooth across that, right? So if there's that's like a thing that obviously shouldn't have been affected causally by the discontinuous jump from one boundary to the other. And so what we'd hope is that the conditional mean of that characteristic is smooth. It's predetermined effectively. It shouldn't have a causal link from one to the other. If there was a jump, then you'd worry there's some other feature about that characteristic, that is something underlying about people on one side versus the other. Oops. So that's kind of exactly what we're doing here. What I wanted to do as an aside, I know I've done some asides already last time talking about non-parametrics, but now that we're like deep in the weeds on how we're presenting this, I want to do a couple of slides talking about how to present this data. So I showed you this graph here, and I think all of you have potentially seen these types of graphs before, and we've talked about versions of this that you didn't really blink when you looked at it. But what is this data? What is Lee plotting here? Well, there's a line, there's this dotted thing where it's the cutoff, there's these points. What are these points reflecting? What are the points? What's going on when we plot this data? So let's talk about that very quickly, because this is very innocuous in some ways, but ends up being one of these really kind of awkwardly important aspects of how you present your data. So one of the best things about RD is how graphical it is, or at least for me personally. So I think for a lot of folks, they find it very transparent and it's easy to see what's going on. And so the question is how do you present what's the right approach to presenting these things graphically? And so it's really worth noting the raw data for the Lee paper is kind of hard. It's not really that informed. Now, I think the Lee one has this particularly striking jump here. And so it's actually pretty good, all things considered. But there's a lot of RD papers where the raw data itself is just challenging to see what's going on. It helps that this variable is continuous. In a binary case, it's almost impossible to see what's going on. But in this one, so here I'm literally plotting every data point. And the margin of victory is on the x-axis. Here's the vote share on the y-axis. What's remarkable is you can actually see the jump, right, that happens. You can see there's this discontinuous aspect in the vote share in t plus 1, the probability of winning next time. But the signal to noise ratio is kind of low, right? You could probably get more out of this than what you're getting by plotting the raw data. So ideally what you do is you'd plot a version of the scatter plot, but you'd focus on means within binned areas. And that's exactly what we did in bin scatter, right? Bin scatter is just the natural extension of this, but in the setting thinking about, bin scatter is just in a broader regression setting. This is actually like we're doing this for a very particular application, which is showing this jump at a cutoff. And so the same problems that came up in bin scatter should come up here, which is how do we choose the bins? And we talked about this for histograms and thinking about kernel regression. The trick is that for the kernel regression, we only really needed, when we were thinking about RD, we really only needed to do it at the cutoff. And what's here is you're doing it over over many points. And so how should you choose your bins? So that graph I showed you from the Lee paper, if you read his figure notes, he says, okay, or his paper, he says, well, we're using 5% or half a percentage point bins. So he cuts every point up into equally spaced half a point bins, and then takes the average between them and then plots the averages. That's what this graph is. And so one thing just from a formal, this moves from like a true thing that you need to know to a presentational thing. In this graph is much less compelling than what he has in the paper. And so why is that the case? It's because the y limits, basically that's what you call it in R, but the y-axis runs from 0 to 100, right? So it's running over the maximum of what the underlying data is, but not the conditional mean. So it looks a lot flatter than it would have been otherwise. When you actually do it how he does it in the paper, he looks from 30 to 70, which is just the min and max over the range he's interested in. And then so you see a lot more of what's going on here. Another thing to keep in mind is that he's windowed the data. So I'm doing just the same thing that he does in the paper. The margin of victory can be much bigger. It can go all the way down like to negative 100. But since he wants to focus on this thing, he's chosen what I'm calling a window around the data that kind of makes this point compelling and is sort of less noisy because there's more observations. That choice of window is kind of not innocuous because it sort of removes distracting features from the data, but it also kind of hides aspects of the underlying conditional means that might be relevant. What's important is that the sort of the choice of bin is, this should be choice of bin, is non-trivial in the sense of like how big the bins are matters for what it looks like. So, this looks a lot smoother than the other one in the sense that this is bins of 4 percentage points. So here what we have is we have very smooth bins with the jump, and then we have kind of this smooth thing afterwards. And here's, oh no, I messed it up. Damn. Okay, well, so I messed up my graph. But so when you do it with 0.1% bins, so 10 basis points, you get a much noisier graph. So you get a graph where when the bin width is 0.1% is that you have a lot of small points. Let me just show you, because since I did all the work to do it, I know it's not, I'll fix it in my lecture notes in just a second. Here. So if you do that here, then it looks like this. Sorry, so then it's much noisier, right? So you get this much bigger jumping around. So this is This is much smaller than what he did. He did half a percentage point. This is a tenth of a percentage point. Smaller, it's obviously much smaller. It's 20% the size, but it's not that much smaller. So there's this interesting aspect to which there's this tuning that goes on here. This is still quite compelling, frankly. I mean, he has a very nice experiment, but the tuning of these graphs ends up playing an important role. You want a compelling figure, right? So, let me go back to the slide, sorry. So given that, there's this important question now of, okay, well, the trade-off in the number of bins really comes to this trade-off between bias. So more bins helps us get closer to what the true conditional means are, right? So this is this tension in the non-parametric estimations. The smaller the bins you made, kind of the less bias there was, but there was a lot more noise because you have less observations within each one. And so less bins basically increases the number of observations and lowers the standard errors within the bin. So now I've told you, given graphically how important bin choice is, there's a nice question, which is to say, all right, well, how should we choose how to do our bins? And there's kind of two important decisions that come up. So these are the natural things that in this literature you have to know and think about. In the end, you can kind of just go with the default, but you should at least understand that these are choices that have to be made. One is, how should you place the bins? So should you equally space them or should you quantile space them? So what does that mean when I say that? So it's a little bit arbitrary, but really the intuition is, when we did it with the Lee one, we said, okay, we're going to do half a percentage point bins, right? So we're just going to divvy up the space in half percentage point bins. But remember, there's an underlying density such that in some places, a half percentage point bin has a lot less observations than other parts of the distribution. And so doing equally spaced ones is going to give you more or less observations. Versus quantile spacing is saying, well, what we're going to do is equally space them in the CDF space. So what that means is we're going to make it so we have the same number of observations within each bin. But that means then if the CDF isn't, or the density isn't uniform, then what's going to happen is you're going to have less points in some place and more points in others. So in my view, the quantile space binning is kind of more transparent because you're kind of highlighting that there's where the data is. But it's a little bit, you can kind of be explicit on which one you're doing. This is in the Lee case, I'll just flip between the two of these. This is doing quantile spaced versus equal spaced within this region. So this is 20 bins on each side, and I'm just doing quantile versus not. What it turns out is when you look within this margin, it's pretty uniform. There's not a huge amount of variation. It does move stuff a little bit, but not enough to really change things. It can change things a lot. With the place where it plays a huge role, and it's very important to keep this in mind, is if this part of your density or the part of your running variable where the cutoff is very low in number of observations. So if it's relatively low in observations in that part of the space, then depending how big your window is, that can play a big role, right? The bigger your window is, kind of then this method is going to want to put, the quantile method is going to want to put very few points around your cutoff, which is going to make it not very transparent. So it actually turns out it's kind of, if you're thinking about quantile binning, the problem is that then you need to think very carefully about what the window is that you're choosing for when you do this. Any questions on that? Does that make sense? That's a sort of subtle, but actually I'm being really kind of pedantic about this because this is sort of stuff that is subtle until you then have to write a paper on it and you're like, oh my God, what am I supposed to do in this setting? And it just ends up mattering quite a bit because you want to know, like, what is well, I don't want to do something arbitrary, but it really, no matter what you do, it's arbitrary. So it's worth kind of going into this with eyes, like clear eyes on sort of what's going on here. So that's the first question, is how do you place the bins? And then the question is, how do we choose the number of bins that we want to use? So, can we choose optimally, quote unquote? And here's where things get a little complicated. So, if you do, well, so if you're choosing the size of the bins and you do equal spacing, you don't need any algorithm, right? You've already presupposed it, right? So if you're like Lee in 2008 and you say, I want to do half percentage point bins, you've already decided what your cutoffs are, right? What I'm saying is, say you choose to do equal size, how equal size should it be? Should it be one percentage point, half a percentage point, et cetera? Canonical, basically, they have a very nice write-up about this whole approach where they kind of talk about the two ways that they argue for doing this, which are very reasonable. One is what's basically called the integrated mean squared error minimizing approach. And the other one is what they call mimicking variance. So the IMSE approach is, what it's doing is it's trading off between the bias and the variance in the choice of bins. So what it's really saying is, look, I want to choose a number of bins such that within each bin, when I calculate the mean squared error for those bins over all observations, I want to basically find the minimum of this. So remember, the mean squared error is the sum of the bias and the variance, right? So what I can actually see what it's trading off between, because I know what the true values are and I know what it's approximating. I can see the bias and I can see the noise around them as well. And it's trading off between the two. But the kind of key caveat, so this is a picture of it on the right here. This is exactly what the picture of it looks like. It's doing, this is the IMSE minimizing approach with quantile spaced bins. And as what you'll notice is it does it for a lot fewer, it picks a small number of bins in this setting. And part of the reason it does this is because it's doing the IMSE minimization over the whole data range. It's not just doing it near the cutoff, which is really what you care about in the end. So what it ends up doing is it ends up picking very smooth looking functions. So in this case, it wants to pick bins that look very smooth in order to kind of minimize the variance. But in some ways, it doesn't look very transparent. It kind of looks like you're masking a lot of the data when you do this approach. When you end up doing this, it basically is a function. There's some constants that scale this, but it's proportional to n to the third. So if you have 100,000 observations, it picks 10 bins. And if we square that, so if you have, what did I say? If you have 1,000 observations, you have 10 bins. So if you have 1,000,000 observations, you have 100 bins. That's the kind of the scale of did I do that right? Yeah, I think maybe not. I don't know if I did that. I can't do third. I can't take to the power of 3. The point is it scales, but it's giving a lot fewer bins. It smooths a lot in this setting. The other approach that you can do is, this is a relatively new one that I hadn't seen before, which is what's called mimicking variance, which is what it's trying to do is it's trying to mimic the underlying variance of the raw data in the binned plots. So this is really nice. This is what it looks like in this setting. What it's trying to capture is the fact that when you take these averages, if there's variance, it's going to, when you smooth it out, when you pick these small bin sizes, you're really going to kill down the overall variance. And so you'd like to be able to show some of that. I mean, ideally in the end, the reason why we don't show the raw data here is it's just very hard to kind of see what's going on underneath. But at the same time, it's very valuable because you can kind of see, well, how much variance is there and how much sort of signal is there. And so the extent to which you can kind of mimic that in your underlying choice of bins, that can be valuable. And so what this is doing is it kind of trades off to kind of keep comparable variability within the regions that you're picking so that the variance of these points looks similar to the variance of the underlying raw data. And so in this setting, it's proportional to n divided by log n squared. So in this setting, if you take this, say if this was log base 10, then if you did 1,000, you'd have 1,000 on the top, and log of 1,000 base 10 is it's 3, right? Did I get that right? So then it would be 3 squared, so it would be 9. So this would be like 100 bins in this setting. So substantially more bins in this version. And so there's different reasons to choose these different ones. What's interesting about it is, well, I'll get into this in a second, but there's different ways to choose this. And so there is some plugin software to kind of look at this. In the case of discrete random variables, this isn't complicated, right? You just bin directly on the discrete random variables. And what's complicated in that setting is that you're going to impute a smooth function on top of these discrete variables, and that's going to make it a lot harder. You have to impute and extrapolate. The one feature I want to say here is that, graphically, this stuff matters a lot. Like it matters for you all to be able to publish a paper that is accepted into the literature. You want to have a credible way to defend your research methodology. But how we plot these data on the left, so over here and over here, is almost irrelevant for the purposes of actual estimating what's going on. What really matters is non-parametric estimation at the cutoff. So what's important to keep in mind is that everything we're talking about is kind of a meta way of discussing the credibility of what's going on here. What you want to be able to show is kind of demonstrate that there's smoothness and continuity of this running variable at other points, such that when you have this jump, it looks like a kind of a very credible thing. If instead what you have is a function that moves around a lot, right? So if we think about our underlying, estimate of our function, and sorry, that's a terrible guy. If this is what we have, so maybe you guys can or can't see, I'll change that. All I'm trying to say here is that if you have, this is a very stylized example, but like, if this is your expectation function of y conditional on z, and it's this wiggly function, and then I say, hey, there's a discontinuous jump at this point, you're not going to believe me. I mean, that's just like not a very credible RD design. Part of me would say, well, it looks like all you did was you kind of just put a line arbitrarily and it would have gone up like this, just like it did before. So from a credibility standpoint, what you're trying to do is show graphically in a convincing way that A, the way that you chose to bin your data isn't masking variation like this, and B, that you have relative smoothness in this underlying conditional mean function such that the jump that we see at the cutoff is actually a treatment effect. Is that clear, folks? It's kind of like it's almost a rhetorical thing, right? I mean, there's an element to this that this is very statistical, but it's really you're trying to present a convincing case for your design. Okay. Like I said, in the discrete case, not complicated. So now we're back to checking for balance. Sorry, that was an aside about how to estimate this. I want it to be clear, you should be able to do this. You don't even have to kind of do all the work yourself. There's very nice RD plot software that lets in RD Robust where you can do this. But at the same time, once you know kind of the number of bins that you need and the size of the bins, you can just take means yourself, right? This is not a complicated exercise. You can do it yourself. It's really the optimization that is the challenging part. The key test is to compare the averages at z equals 0. That's at the cutoff. So that was what we were talking about, is we were talking about the continuity of those covariates across that cutoff. And there's this very nice paper by Canay, I'm not sure if that's how you pronounce it, but Canay and Kamat in 2017 in Restud, in the Review of Economic Studies, that show basically if you're willing to make slightly stronger assumption, which is really what shows up in the Lee 2008 paper, that you can do better than just looking at averages across this cutoff. So this is really the idea is that, what we're saying is we're looking for balance in the averages of other variables. That's what we did, for example, when we were talking about looking for balance in IV or in Bardic or any of these things. When we have this treatment thing, we think that there are characteristics that should be balanced between the treatment and the control group. And that's the analogy that's going on here as well, that there should be continuity of these characteristics at the cutoff. But the point is that it doesn't just have to be the mean. In the same way that for a randomized design, the averages are not the only things that are balanced across this if something is truly randomized. In fact, it's the whole density should be comparable between the two of these. We should be able to even just permute labels and effectively look at the distributions and see what the relative density of characteristics look like. And so the Canay and Kamat paper is basically saying that you can do a lot better than just looking at mean differences and get a lot more power than you would by just looking at mean differences. There are certain types of variables, for example, where mean differences are not nearly as powerful for looking at things, maybe because there's kind of there are parts of the distribution that are getting shifted around that don't really move the mean, but actually do affect what the underlying distribution looks like. And more importantly, they basically show that there's a way of doing these tests that are using permutation tests that are going to be really much more, their size it's better controlled. So by that, I mean that they are going to have correct rejection probabilities relative to sort of standard asymptotic tests because, and that's a concern that they're worried about because the number of observations near the boundary is really small, right? So even though we may have 2,000 observations in our RD analysis, once we put a bandwidth of 5 on each side, we actually have a relatively small number of observations, right? So think about this context here with the Lee paper. There's a big cloud of points, but as soon as we do within a bandwidth of 2.5 or 3 around this cutoff, we have a much smaller sample size. Our effective sample size is substantially smaller. And given that our asymptotic argument is letting it get close to 0, we're going to have always kind of have a relatively small distribution compared to the overall sampling process. So they have this very nice permutation test, which has some very good statistical properties, which they basically, the intuition is that covariates should be approximately identically distributed on each side of the cutoff. With the idea being like, look, all you're doing, you're basically randomizing who's treatment and who's control once you get to the cutoff. And so we should have similar distributions across the two. But with the key caveat that this is not exact, right? It's an approximate argument because the running variable has an effect on the outcome. So the distributions are not identical until you get right to the cutoff. This is an asymptotic argument, in fact. And so this is what the test would look like. This is actually from their paper. This is why the graphic looks so ugly. I can never get these things to look good when I put them in from I save the picture from them and they look awful. Sorry. Anyway, so on the right is that graph that we saw before, right? So this was that balance check that we did where we said, let's look at the difference in the vote share and then the mean Democratic vote share in the period before. That was that test that I did. And I said, look, you can kind of see it smooth through this. And it's a very nice way of looking at this, right? So this is just literally, we're looking for a test in the continuity of the expected value of the characteristic. What they're doing here in this left picture is they're saying, okay, well, what we can do is we can talk about actually testing the whole distribution. So this is the empirical CDF of that characteristic. So here's the Democratic vote share, which is this variable here, and you can see the conditional, the cumulative distribution function for the left of the threshold and of the right of the threshold. And obviously you have to pick what the threshold is. But what you can do is kind of compare what the difference between the two of these looks like in order to test whether or not this satisfies the assumption. Yeah, I think there is a little bit of I will say about this paper, there's a little bit of a taking your toys away aspect. What I haven't done with this, so one of the interesting things in here in this empirical example is they kind of show that the Lee test, this thing here, where it looks pretty smooth, they reject this one. So this, this is not balanced. Under like the CDF is not balanced. They're not equivalent. So you can kind of see that here. I know this is a crappy graph, but like you can see that the distinction between the two is not perfect. And when you do the permutation test, you actually reject the null that they're equivalent at like the 4% level. So, oh, shoot. So that's interesting. I think that it is a little bit hard for me to wrap my head around it because it looks very smooth in this. So like there's this question of what's some good examples of something where this is satisfied. I'm a little bit nervous. Like I don't totally know in this setting. I don't have a lot of examples. I know only the kind of this main one. I haven't looked at a lot of empirical papers, but this is really a set of tests worth knowing. The test on the right is kind of the one that's easily worth doing. But if you really want to kind of be robust, is you can do these tests, which are formally kind of a lot better measured and have much better statistical properties. That being said, I haven't used them myself. Really kind of, it's a slightly stronger assumption that is pretty reasonable that's necessary from that paper. Basically, you're assuming that things are permuted across the cutoff such that the covariate distribution should be continuous at the cutoff. Nice thing is that there's code available both in Stata and R to implement this stuff. Another test that is very important to do is basically, it's similar to the balance test. What's interesting about it is it's a kind of like a balance test of the running variable. And this is called the McCrary test, just named after Justin McCrary, where they're proposing a test of the continuity of the density of the running variable. So in essence, is there bunching in the characteristic on one side or the other? And it makes sense economically that there would be, right? So if there's a benefit of being on one side, why would you not shift yourself across the boundary? So a good example, there's an example on the right, but another example that kind of makes sense is test scores. So you think about kids who are passing grades. My co-author, Will Doby, has a nice paper where they look at stuff in Texas, and effectively, there's huge amounts of bunching on the passing side of a test cutoff. And that's because there's effectively manipulation on the part of the teachers to make sure that individuals are passing. Once there are important economic reasons to go across these boundaries, you start to worry a little bit about the discontinuous aspect of this. This is basically the way that this is done. This is from the McCrary paper on the here. Is what this paper is doing is it's estimating densities, and what it's doing is, so they have an example where the McCrary test passes, but this is one where it fails. So where it fails is bills taken in the U.S. House of Representatives. What is the percent voting in favor of a proposed bill if you look at the density of the vote share for one bill versus the other? So as you might imagine, bills that are going to lose by very close margins don't get brought up in front of the House. So what happens is that there's a density of bills that are going to get passed. And then as you get very close to the cutoff, there's manipulation in terms of they really, they make sure that those bills are going to pass. And there's a lot more bills that are right on the right side of it than on the left. Basically, there's this discontinuous drop right to the left of the passing threshold. And on the right, the kind of density looks similar. And then there's obviously this density of 100% passing ones. And so the way that you run this from an intuitive standpoint and just econometrically is, we talked about estimating densities on the left and on the right. All you would do is estimate the density basically coming in from the left and the density coming in from the right and compare the two of those. The difference in those densities is a test statistic, and you can test to see whether or not you reject continuity in that variable. Fortunately, you don't have to write that code yourself. There's just a very nice statistical package in Stata and in R to do this sort of exercise. I guess I'm assuming everyone on this call uses either Stata or R. If you're a Python or Julia person, I'm sorry that you're out of luck. But someday, this code will be available in those. Just the fact that it's available in Stata is kind of a huge deal. This is not an end all be all, this particular test. So one thing, there's a paper that we'll try and talk about on Thursday, which is by, I'm blanking on the names, where what they're doing is saying, okay, imagine you have this manipulation. Can you talk about bounds as a result of this on treatment effects? And so can you still use this RD even when there's manipulation in the running variable? Okay. Any questions so far? So that was testing for bunching in the forcing variable. There's kind of a slightly less formalized approach, but one that I think is quite compelling, and I think comes from this Ganong and Jaeger have this paper in JASA where they're actually thinking about what's called regression kink designs. But really the idea is a very intuitive one. And from talking to other practitioners, I know this shows up in other places. I just don't know as formalized of language to talk about this. Caneo definitely has one paper where he sort of talks about this, but not in the way that Ganong and Jaeger do, where it's just the following. So remember, we were talking about this kind of RD that happens at 50%. I mean, it's basically 50%, right? If you're winning in an election, it's not quite 50% if there's a third party person, but there's some cutoff rule. And the idea is, well, what if I randomly permuted what the cutoff was? So there's basically placebos one could check, right? So if the cutoff is 50, so say we go back to here, let's just look at the raw data. We could imagine saying, all right, well, let's make the margin of victory -10 and do the same estimation procedure from the left and on the right for -10, get the coefficient effect there, the relative difference. And we could do that even in a bunch of places, right? We could permute this boundary across a number of different thresholds across the support of the margin of victory. And then look at the effect that we estimate relative to the that permuted set of values. That's basically what we're doing in these. That's a lot of times gets called like a placebo test, but inherently, if you remember back to the beginning of the semester, that's what we're doing when we do these randomization inference tests, where we were permuting who's treated and who's not treated. We were kind of relabeling and then re-estimating what the effect is in order to get ourselves a null distribution of no impact. So in this context, what we're doing is permuting where the threshold cutoff is and then saying, well, if there's no impact from thresholds, where, what would the underlying null distribution of thresholds look like? And where does our effect lie in this null distribution? Does it sort of look like a statistically significant outlier? The challenge in this setting is that, as you might imagine, so think about our cutoff here in this setting, is that as you permute stuff and it's too close to where this treatment effect is that we actually think it's happening, that there's kind of this overlap problem of how we estimate things. So if we want to get far enough away from our treated cutoff that our bandwidth doesn't overlap with the treatment effect and kind of bias our estimates. And so that is just something you have to keep in mind that shows up as an issue in my setting, in some settings that I've worked on. But I think it's a really nice way. I think it's very intuitive for practitioners. I think it's less developed. It shows up really well in this Ganong and Jaeger paper, which is about RKD. But I really, from reading that paper, I see no reason why you couldn't do that in the RD setting as well. Okay, so finally, we plot our outcome. We show our outcome. So, right, so we've done all these things. So basically we spent 50 minutes. This is what most talks, by the way, are like. If you haven't given a lot of talk, it's 50 minutes defending my identification strategy, 10 minutes of showing you what the result looks like. And what you finally do is you basically say, okay, let's look at our outcome. So we plot our outcome, and that involves the plotting of our bin data as well as the choice of the conditional mean function. And one of the things, I touched on this earlier, is that, remember, we're plotting this large window around the cutoff, but the window that we do for this, so this is this graph here, this is from that Lee paper, right? So the window of graph that he shows is from minus 0.25 to plus 0.25. But once we do local linear regression, the bandwidth that we're going to choose is going to be much smaller than that cutoff that we're going to do. So I'll show you that in just a second, what it looks like for ours. But there's kind of two pieces that is always really easy to forget, especially when you're doing local linear regression. There's a window and there's a bandwidth. The window is kind of like what we're looking at for our cutoff, and it's kind of our way into seeing what the function looks like. And it's important to kind of pick the window in a way that looks good, but it's kind of totally irrelevant for the purposes of estimating what the actual effect is. Because remember, the bandwidth is going to be chosen basically to say, all right at our cutoff to the right, how many data points are we using in order to fit a local linear regression? And here he's doing logit, but I see no reason to do that in this setting. Obviously, he's tenured professor at Princeton, but there's really no reason to do a logit here. You should just do a local linear regression. And so the way to think about this is what this window and this graph is doing is it's really an eyeball test to some extent. So Cording et al. Have this really nice paper about visual RD. It's this idea of we can kind of look at RD and see whether or not we think something is plausible. And so, a good graph is worth a lot in these settings. If you have a bad graph, you might have a bad experiment, unfortunately. What's really interesting about this Cording et al. Paper is what they do is they actually use experimental data. They take papers, they like simulate data where there's real RDs and not real RDs. And then they have normal people, not people who sit and take econometrics classes, look at graphs and decide whether or not there's actually a cutoff at some threshold. And what turns out is that people are pretty good at the binary thing of saying, oh yeah, there's a cutoff there, or oh no, there's not an actual effect in the. Now they can't get the point estimates right, and they certainly can't calculate standard errors, but they're pretty good at the binary thing about whether or not something is really significantly different from zero. And what's interesting, and this is what we're going to talk about on Thursday, is that intuition really comes from consistent with this kind of honest RD thought process of saying like they're pretty good at kind of looking at how smooth a variable is and figuring out, okay, how likely is it that this is just generated by imposing a functional form versus something that's like a true discontinuous jump. I think this paper is really nice. The actual estimation process in this, remember, is subject to a lot of tuning parameters. So there's the choice of the estimation procedure. So I've been harping on you guys about local linear regression, but you could be doing other types. You could be doing logit, as we said here. There's other types. There's global fitting, etc. There's choice of estimation procedure. There's the bandwidth. There's the kernel. There's a lot of things that are more automated now, but there's still a lot of discretion, especially as you start doing these non-parametric methods. Use all these tuning parameters you have to worry about. And as you let things, once you want to kind of allow for more complicated things, there's just more and more tuning parameters you need to do with. My suggestion to you is to use defaults unless you have a really good reason not to. So the defaults tend to be, or these are at least my defaults, and is basically, do local linear regression, use the optimized bandwidth from one of these estimation procedures in the packages that are really coming from these papers. So Canonical and all have this really kind of large suite of software packages called RD Robust. Kolesar and Roth have this RD Robust R code as well. And in my view, actually, I think the uniform kernel is a lot more transparent about what's going on. Actually, the default for Canonical et al. Is the triangular kernel. There are some statistical reasons to do that. But with the uniform kernel, you kind of know, like, the bandwidth maps directly to the number of points that you're using. When you do the triangular kernel, you kind of have to think about the trade-off that's going on there. That being said, you can tell, like, that's already right there. That's like a choice that I'm making versus someone else. And so that's going to have issues. So even in those categories, there's discretion. And so the point is, it's really important to be kind of consistent and transparent in what you're doing. If you're interested in kind of thinking about this bandwidth snooping problem, Armstrong and Kolesar have a nice paper about this as well I think in quantitative economics. So, one really nice thing is, when you do this, it's just kind of my new hobby horse. When you do this estimation procedure, you can kind of just put your estimates directly on the graph. Stop like wasting time with these tables. Just put you have a graph here, there's an estimate, put the coefficient here on the table. or like directly in it. You don't need to make like a separate table that does it. You can kind of just show us all the graphs that have it and the corresponding estimates. Your mileage may vary, but this is kind of, here's exactly this effect. We see that there's basically this almost 6% jump that's statistically quite significant in this setting. In this context, it was not purposeful, but I basically omitted the underlying. A lot of times people will do this and plot the underlying conditional mean. That one would look like, let me just do it so that we have it here. It would look like this. Why did I think this one? This one. It would look like, sorry. That it's in here. It would look like this, right? So now you kind of have the smooth variable. The red line is the conditional mean function that you're doing with local linear regression. It's really the difference at this point evaluated at z equals 0. That's the effect that you're estimating. But you have the underlying points to kind of see what the underlying data looks like. Sorry, I need to update that graph so that it looks, you really should have the underlying conditional mean on there because that's the relevant piece for the estimation. Any questions on that? No? There's what was I saying? Okay, so there's this estimated effect. Sometimes showing robustness, the only way to convince someone is, doing the optimal is not a good excuse. There are basically, we estimated here this effect of like 5.88. Well, that was with a particular chosen bandwidth that comes optimally from this selection strategy. But what you could say is, okay, well, how much are you worried about bandwidth affecting my result? There's a natural point that as you have a smaller bandwidth, you're going to have more bias, more noise, but potentially less bias. As you increase the bandwidth, you're going to have more bias and less noise. And so typically here, what this method is doing is trying to trade off between the two of these, just for the purposes so that you know what this is. This is a bandwidth of about 6.2 or something. So what I did is I just re-estimated over this setting where I ran the bandwidth from 2 to 10. And I said, okay, well, how does it change my estimates as I do this? You can plot it in this very nice way that kind of shows this trade-off and kind of how sensitive your methods are to these different approaches. I think this is like a very clean way of kind of highlighting the sensitivity. You could go with it's not just about showing something being statistically significant from 0, right? It's quite plausible that there will be versions of this where, for example, you let your bandwidth be 2 or 3 and it's not statistically significant. It's just there's not enough data. And that's fine. But it helps to be transparent in this point and being like, look, what we're doing is we need to trade off so that we have enough power that we're able to estimate this correctly. While showing that the magnitude of it potentially doesn't shift dramatically. So I think that's really important. I also want to emphasize this graphical way of doing it because I see a lot of people plot like a table where they do 100 of these different things, and you could do so much on one graph, kind of showing, if you're doing it for one outcome, you could show 100 different versions of your robustness test on this one thing. And it's so much more compelling because you can kind of compare across the specifications, what's going on. Great. Okay, that's it for today. We are going to do one more day of RD, I think, just because there's so much stuff there. And I have talked myself into the idea that it's worthwhile for you all to be experts in RD at this point. So let me stop there. I'm